system, so take it away.
Thank you. Welcome all. I'm John DeGoes, and today I'm going to be speaking about the design of the new Scala 8 effect system that I've been working on for quite some time. I'll give you a brief intro to what this thing is about, so hopefully entice you not to leave in the middle of my presentation before I get to the good parts. And then I'm going to give you a tour of the work that I've done on this new effect system for Scalaz 8. And then I'll show you some benchmarks and other types of things. So how does this compare with the other stuff out there that you may already be using from a performance and safety and expressiveness standpoint? And then finally, I'll wrap up. So about me, I program with functions. And in fact, I contribute functions to open source projects, and I start companies powered by functions. I love functional programming. I was about to walk away from programming forever before I discovered functional programming. And then I discovered this, and wow, I found a world in which I could actually reason about the software that I wrote, and I could build things that I was really proud of. And that just blew me away. So yes, I am one of those functional programming zealots that you probably read about. In fact, let's be honest, you probably have read about me. Yes, I wrote this article on removing if statements from all your code. I wrote this one in which I argued against using data structures. And yeah, I called descriptive variable names a code smell. I may have said something about Twitter once or twice. Sorry about that, Twitter. Can I get my blue check verification thing now, please? Pretty please. But it's time for a reality check. I love functional programming, as you all know by now. But how many people in this room do pure functional programming at their day job and are paid to do so? Okay, great. Yay, go us. All 6 of us. The reality is that most Scala programmers don't program functionally. That's just a fact. And in my opinion, it comes down to this following graph that I've made. Pure functional programming is like a lot of things in category theory and algebra and mathematics and so forth. It's very useful for us as developers because it helps us reason about the software that we write. It helps us make correct software. But this stuff it's directly beneficial for us, but it's only indirectly beneficial to the business. Because the ROI of us understanding our programs better and being able to stitch things together better and being able to have some idea that they're correct is not easy to measure. Whereas if you take a lot of other technologies out there and other paradigms like Akka and Spark and so forth and different abstractions that you use in your day-to-day programming, a lot of those convey immediate, like actual measurable benefits to the business. People use Akka because they can stand up distributed clusters that just run with supervision and all that stuff, and that solves a business pain right away. And don't get me wrong, by the way, everything that directly benefits you as a developer indirectly benefits the business. And everything that directly benefits the business also indirectly benefits you because it's stability, or it's good for your career, stuff like that. It's good for your team, good for growth in your department. But where we really want to be is the top right-hand quadrant of this graph, where we're doing things that help a developer reason about their software and build correct code and so forth, and directly benefit them, make them a better software developer. But also things that directly benefit the business. They have a direct impact on things that matter, bottom line things that matter to the business. So for today, I want to take a step back and let's just pretend we hate functional programming. Throw away all that type safety and composable stuff and equational reasoning, just throw it all in the trash can. We're going to think like a business person. And what I want you to do is go through this scenario with me. Let's say we're building some sort of modern fancy microservices architecture, and we get these requests, thousands of requests that come in every second. And these requests, we have to parse them, and then we're going to end up doing a bunch of things. We're going to make SQL queries based on these to the database. We're going to load some stuff from cache and do more query if we have to, if it's not there. We're going to call other microservices APIs running inside our infrastructure. We're going to call third-party APIs. We're going to do all this stuff. And what matters to the business is being able to handle a lot of these every second. And also being able to decrease the latency, because for most types of business, 900 additional milliseconds translates into millions and millions of dollars of lost revenue. So in the ideal case, what we want to be able to do is handle all these different requests and sort of explore this graph, do it all in parallel, and then if something goes wrong, like let's say one of these SQL queries that was critical to the success of this service fails, and we have to return an error back to the client that initiated the request. We're going to do that, and we're going to shut down all the other computation. We're going to clean up all those resources. We're going to stop reading megabytes or whatever it is from all these different places. We're going to stop that right then and there as soon as we know we're going to fail. And as a result, we're going to conserve resources tremendously, and we're going to minimize latency because we're very aggressive in doing this in parallel to begin with. And this type of scenario is super common. You've probably had to work on something like this. And most likely you've had to make trade-offs because of the tools that you were using that the business didn't want you to make, but they were sort of forced to because you didn't have enough time to solve this in the right way. What are the really big pains here? Well, we have asynchronous code, and lots of it, because we don't want to block threads that's going to suck up native threads and kill our performance. We have to handle thousands of requests per second, so of course we're going to need asynchronicity. We're going to do stuff in parallel to the maximum extent possible. One request could come in and kick off like lots of different threads that we use here and there as we're going and satisfying all the business needs of this request. And then we can't leak resources ever, because if we leak a thread one time, well, we're going to leak it again, and eventually we're going to bring the production server down. Not just threads, but sockets and all these other things. And then we want this thing to be really, really fast so it's not constantly falling over and costing us lost revenue. We want all these things. And these are business pains. They're big, meaty business pains. And if we solve them, then we're in business. Like we make the business happy. And ideally, we hopefully solve it in a way that makes us happy too. So this is what Scala Z8 effect is all about. What it is it's a small composable collection of data types and type classes that are going to help you and me, just ordinary developers, build principled, performant, and pragmatic I/O applications. And these applications aren't going to leak resources, ever. They're never going to block, and they're going to scale across multi-core systems. And the heart of this effect system is a new data type and then a runtime system for this data type, which is called I/O. And in case you haven't seen anything like this before, you can think of I/O of A as being a better version of future of A. What I/O of A is, at its essence, is nothing more than an immutable value. It's just a value. It's like Scala list or Scala option or something like that. It's nothing more than an immutable value. And this value describes an effectful program, so a program that interacts with the outside world that either produces an A, it's going to fail with a throwable, or maybe it's going to run forever. That's what an I/O of A is that immutable value that describes an effectful program that produces an A, throws some sort of error, runtime error, or just spins forever, runs forever. That's what it is. And every single method on I/O, we're going to explore some of them today, they're all exactly like the methods on list. They're always going to return you a new data structure, a new I/O. They're never going to mutate anything. There are no effects. Everything you're going to see today is going to be purely functional. And if you keep it focused in your mind that this is nothing more than an immutable data structure, you'll follow along just fine. So what does it help us do? Well, ideally, it helps us build these, very quickly build these asynchronous, concurrent, and leak-free performant applications, which, by the way, happen to be type-safe, purely functional, composable, and easy to reason about. Shh. So let's go on a little tour of Scala Z8 I/O. And what I'm going to do is I'm going to show you all the building blocks inside this I/O data type. So all the primitives, you're going to see them all today. And I'm going to show you more than just the primitives. We're actually going to derive some of the advanced functionality inside this library using these primitives. And you're going to see firsthand what it means for functional programming libraries to be composable. When things have the right shape, when you separate the concerns and they snap together like Lego blocks, you can assemble them to solve tremendously complex problems in a very straightforward way. And you're going to see some of that today. So how do we run these things? Well, it's just a data structure. What you can do is, if you want to run an I/O program, you use a runtime system, which is baked into this trait called SafeApp. So all you have to do is extend this from your application, and then presto, you return an I/O of unit instead of unit. That's the only difference. So you're returning a description of your program instead of actually doing the effects. And then in this particular example, there's a little bit of code that asks you what your name is, reads your name, and says, hello, John, or whoever, good to meet you. This is an interactive, effectful program. And yes, it looks a little different, probably, than what you're used to, but it does all the same stuff. All you have to do is put up with the fact that it's going to be a little bit different, a little bit more similar to the style of programming that you're used to with Future and abstractions like those. I/O has a function called apply that's capable of taking a pure value and lifting it up into an I/O of A. So if you have an int, you can lift that right up into an I/O of int. It has a function called map, just like collections do, an option, which takes an I/O of A and turns it into an I/O of B by allowing you to specify a function that takes an A and turns it into a B. So if you have a program that builds an A, you can turn that into a program that builds a B by mapping over it. Of course, these programs can be sequential, so they support this flat map operation, which allows you to describe two programs in sequence where the second one actually depends on the value produced by the first one. And this thing is called flat map, and it allows you to build sequential programs that depend on results of prior computations. You can produce a program that fails with the fail combinator. Just specify a throwable, and there you go. You get back an I/O of that A, where A can be anything, it's unfixed, and that program represents failure. There's no exceptions being thrown here. This is just values, ordinary functions and ordinary values. You can recover from a failed program by using the attempt function, which takes an I/O of A and turns that into an I/O of throwable or A. That funny little symbol right there is Scalaz's disjunction data type. And I know what you're thinking, why the heck did they use that symbol there? They should have used Unicode. Well, if you can go from an I/O of A to an I/O of throwable or A, you can also go the other way. And this combinator is known as absolve. And it just submerges the failure into the I/O data type. And we're going to use this here in a second. And this we derive. We can also, using just the stuff we've seen to date, create this or else combinator, which will do this I/O of A, or if it fails, it's going to try to do the other one. And this allows you to create actions that represent recovery. Either we're going to open the primary data file, or if that fails, we're going to open the secondary data file. And look at how clean and elegant that is. Me just building data structures. Open this or else open this. And this is derived in terms of the other ones. This I/O type wouldn't be that useful unless we could interact with the real world and do some input-output. So of course you can do that with the sync method, which takes some imperative code and imports it into this data structure. It describes that effectful code in terms of one of the terms in the sum type that represents I/O. And we can use it to build functions that describe interactions with the real world. Like here I've built put strline, which prints something to the console, and read strline, which reads something from the console. And of course these functions don't actually do anything other than build a data structure, but still they describe that interaction with the real world so that later on it can be interpreted by the runtime system. And this is all that's necessary to build console programs. Any console program you can possibly imagine, if you can express that as an imperative program, you can express it with I/O. And that's true for I/O in general. There's no program you can build using non-functional programming techniques that you cannot build with using functional programming techniques. It's just one-to-one. The syntax changes a bit, but it's the same thing. So I/O has another function which allows you to import asynchronous effects into your code. And if you've seen something like this before, it's going to differ a bit. Scalaz 8 I/O actually has a different notion of importing an asynchronous effect, one that's strictly more powerful. And what this asynchronous effect constructor allows you to do is specify a hunk of synchronous code that's going to accept a callback. And then later on, it's going to call it when whatever was going to happen does. Netty calls you back with your next chunk of data from the byte stream or whatever. You're going to call that callback with the result. Or if there was an error, you could call it with the failure. But also, this constructor allows you to, it has 3 terms here. The async return, your effect can either say, okay, I'm going to call that callback later by returning later. Or it can say, you know, this really isn't an asynchronous effect at all. I was able to compute the value right now. Maybe it's a cache or something. And so you can return it right then and there. And that is critical for building highly performant effectful systems, because it allows you to say, we don't know if this is going to be asynchronous or not. We certainly don't want to use callbacks if it's going to end up being synchronous. So we're going to execute the effectful code, and then if it turns out that it's going to be asynchronous, we'll call the callback. But if it turns out we could compute it right away, we'll just go ahead and return the value there. And this allows you to avoid stack overflows and avoid expensive like callbacks upon callbacks upon callbacks for the very broad class of effects that it's not determinable whether or not they're asynchronous until you're actually doing the effectful code. And then finally, and this is probably the most important thing, it allows you to return a promise basically to say, okay, I'm going to call your callback at some point later in the future, but if for any reason this computation has to be canceled, then call this hunk of code here to cancel the effect of that asynchronous computation. And what you should be thinking here is, one effect may be reading a megabyte's worth of data across this socket. If we decide we don't need that computation because something else in some other chain failed, we don't want to read the rest of the megabytes worth of data. Or if we schedule something for 2 hours into the future and then we decide that's not necessary, we don't want to have that thing run and perform all its effects 2 hours into the future. So this allows you to, when you're importing these raw base effects, it allows you to specify a way to cancel an asynchronous computation and to remove the runtime overhead of that asynchronous request. And that is extremely important here, and it's a missing step in many of the other libraries out there. Here I give you 2 examples where I use this to build a spawn, which just takes an A and computes it on a different thread by using that async constructor. And then another one called never, which is never going to call the callback. And this is the equivalent of sleeping forever. It's just going to run forever. It's not really going to do anything. But it's a handler that's never going to call its callback. So here's an example of how we would use this. After we hopefully we're using FP libraries that do this for you so you don't have to. But if you have to, you just write a few of these different importers to import the different effects into I/O, and now you can use them like ordinary synchronous code. There's no difference from your perspective. And these effects in general, they're going to mix synchronous parts with asynchronous parts. You don't have to worry about that. It will all execute transparently, even if you have these mixed effects, and also in a performant fashion. In this example, I do one HTTP request, I get back the result, and I do another one based on the value of that. So I actually do need the ability to chain these computations together. And I do all this without any callbacks. There's no blocking of any type here. There's absolutely no blocking in Scalaz 8 I/O, and no reason why you would ever have to write any blocking code at all. So you can minimize your use of native threads. Another primitive that's very useful is sleep. So given a duration, it's going to return you an action that resumes after that specified duration has elapsed. And you could use this like this: time to sleep. I'm going to sleep for 10 seconds, and then I'm going to wake up. Of course, this is not actually sleeping. This is using that async constructor and scheduling this in the background with the ability to cancel it and so forth. And then it's resuming that computation. The computation will be resumed at that point in the future. Given this, we can define a little combinator called delay that just delays any action by the specified amount of time. Very simple. And we'll use this here to build something even more complex. So now it's time to talk about concurrency. I said that I/O included those concurrency primitives inside of it that help you solve real-world problems that matter to the business. Well, what are those? There are a couple of different ways that we could have approached this problem. First off, we could use threads, but the bad thing about native Java threads is that they're at the operating system level. They consume OS resources, and they're very heavyweight, and it's not really possible to interrupt them in a safe way that guarantees preservation of resources. So doing things like doing a whole bunch of stuff and then canceling other stuff, just not possible with the threading model. We could use green threads like Haskell if only we were doing this at the language level, but we don't have that ability. We're not going to write a Scala compiler or plugin to do this, at least probably not. But green threads do have the ability, they're super lightweight, so you can have tons of them, tens of thousands, hundreds of thousands of green threads. They scale really, really well and allow you to build these modern architectures without any pain. They're very, very efficient, but we just don't have that as a resource available to us. So the concurrency model that I chose for Scalaz at 8 is a fiber-based concurrency model. And a fiber is very much like a green thread, except it's implemented in user land. So this is implemented as a library. And they're super lightweight. They actually have zero cost for pure FP. Pure FP imposes its own sorts of costs because you're building these data structures and you're interpreting them to effects later. And it turns out that when you build an interpreter, if you build it in the right way, you can do fibers at literally zero cost. So there's no cost for us using them. And we can define precisely the semantics of these fibers. Because they live inside userland library, we can say, yeah, okay, we're going to add interruption, or we're going to add timeouts, or we're going to add this or that. We can add whatever features we want. We can bake it in at very, very low cost. And these fibers, because they don't necessarily consume a single thread, they'll of course use threads, but fibers will yield to each other under periods of high contention. We can scale them way beyond the limitations of native threads. We can have tens of thousands, hundreds of these thousands of things at a time. Some of them are going to be suspending through async computations and so on and so forth, but we can have huge numbers of these things, and they can yield cooperatively to ensure fair use of resources. So these are very powerful abstraction. I think you're going to see a lot of the concurrency work in the JVM is going to move towards fiber-based models because they're just too powerful to ignore. And then in any concurrency model, you have to choose one or more concurrency primitives. The one I chose for Scalaz at 8 is based on fork and join. It's extraordinarily simple. I can describe it in a single slide, and the semantics are almost as simple as the type signatures that you see here. Fork spawns off an independent fiber. So if you have an IO of A and you call fork on it, you're going to get a fiber of A. And that fiber gives you a handle to something that's running elsewhere. And there are two things you can do with that handle. You can either join it if you want to get its result at some point in the future, like you've done a bunch of stuff and now it's time to get its result, then you join it, which is of course non-blocking, or you can interrupt it, and interrupting will put an end to that fiber's execution. And all resources will be totally cleaned up and released safely. So you may have constructed a big, long imperative program that's doing all these different things. If the result isn't needed for whatever reason, the end of that program, whether it was going to run for 2 hours more or 2 seconds more, is going to be chopped off. And all those resources that you would have had to throw down the drain will now be freed up to be used by other fibers executing on the system. So those are the two things you can do. When you fork a fiber, you can also specify an uncaught error handler. So you fork a fiber, but you want to know if it does something terrible and kills itself and whatnot, you can specify an uncaught error handler, which will be invoked with any errors that fiber issues which it does not catch itself. Here's an example of how we can do Fibonacci sequence using fork join. It's trivial. It's just a couple lines of code. We do the Fibonacci, we call itself recursively on n-1 and n-2. We fork those off, then we join them back together and we add them. And this will suck up all your CPUs. Doesn't matter how many CPUs, there exists a n sufficiently large that we can suck up all the CPUs doing this number crunching. And it's extraordinarily easy to define that. And of course, we don't have to deal with real threads or any of that other messy stuff or leaking resources. This is a very functional, very declarative way to solve that problem. Then another one of the primitives baked into Scalaz 8 is RACEWITH, which is a much more powerful version of the race, or the first completed of, that you've seen in other libraries. And what RACEWITH does is it has two things, and it's going to race them. It's going to start them off independently, and one of them is going to finish first, and the other one's going to keep going. And at that point, it's going to invoke a function u passed in called the finisher. And that finisher is going to be provided with the winner, whether it was left or right, as well as a fiber to the loser. So you get the value, but you also get a handle to the fiber that lost the race. And you can do anything you want with that fiber. In particular, the ordinary race combinator can be defined by killing the other fiber. So you got the winner, now interrupt the loser, and then boom, you save all those resources. Every single other definition of race in any library out there is broken. And it's broken because if you call race on A and B, it's going to run them both to completion. It doesn't matter which one finishes first. You could have hours of computation that you're burning through, memory and threads and socket I/O and all that stuff. And it's all just going to keep on continue. Any first completed of or race combinator in other libraries, they're all totally broken. And then you can also, with this RACEWITH, you can actually, well, here's the definition of race. It's so simple. And by the way, the type signature of RACEWITH tells you so much about what this does. The type signature of race, given IO of A and IO of A, returns an IO of A, doesn't tell you much. There are lots of different ways you can implement that. But this one's so polymorphic that you know what it's doing just by looking at the type. There are strong guarantees here that help you reason about what this is doing. The definition of race is just kill the loser with an error, saying you lost the race. And given this definition of race, we can do a generic, leak-free definition of timeout, which is amazing because all the other timeout combinators out there, they're broken too. We can take an IO of A and we can time it out in a certain amount of time. If that time elapses, then we're going to kill it. And how do we do this? We just sleep for that amount of time and then produce an error. And then over on the other hand, we run it, and then we call RACEWITH, and then we kill the loser, and we're done. And then we absolve the error. So this is a very compact compositional definition of a timeout that doesn't leak any resources, ever. And then, of course, with this same definition of RACEWITH, we can do this par combinator, and this par combinator takes an IO of A and IO of B and runs them both in parallel. And it does it just, there's a few different cases you have to contend with, but this is good. Like these cases actually force you to deal with, I'm running this one, and then this one fails. What should happen? Well, we don't want to waste computation and let this one keep running, so we chop it off, we interrupt it. And then vice versa, it's symmetrical and so forth. And then it's only in the case that both run to completion that par of A and B actually produces a tuple of the results. Retry. Once we've built all these things, I mean, we could just add stuff all day long. It's just so incredibly easy. Retry, it's this action or else retry. And that's going to retry forever until the first success. Or we can retry n if we want to retry up to n times. Very simple. We can retry for a specific duration. So we can retry for up to 5 seconds. There's no mess here. It's just very clean, very simple, elegant compositional definitions that use the primitives that we've already built and assemble them in precise ways. And all these combinators, because they're built on these primitives, they have the expected semantics. So this infinite retry action, of course, it can be interrupted. And when it's interrupted, well, all that stuff that comes after is gone. It's not sucking up memory and CPU and other things. So the fiber concurrency model requires you to have a way to communicate between fibers. One produces a result and you want to do something over here. And MVAR is a standard concurrency primitive for doing that in Haskell. And I basically copied the Haskell one over. I mean, not the implementation, of course, but the type signature. And this MVAR is very low level. It does everything synchronously whenever possible. It will never spawn threads just to spawn threads or use actors or any of that stuff. This is super low level, very hand optimized, very efficient, and it allows you to build other things like channels and concurrent queues, and all sorts of things can be built on top of this, and you can rely on it because it is very well optimized. It's and takes advantage of the much more powerful async constructor that we have in this IO data type that allows you to determine whether or not to do an asynchronous action based on executing some effect. And here's an example where we create an empty MVAR. An MVAR, by the way, is a 0 or 1 element blocking queue. It doesn't actually block in Scalaz 8. It's totally asynchronous, but you can think of it as a 0 or 1 element blocking queue. So create an empty MVAR, and then from another fiber, which we're just going to fork off, we're going to put something into the MVAR, and then from the original fiber, we're going to take it. And what happens is this line here actually suspends until this one runs and puts something in the MVAR so that there's something to take. And I actually don't think this is quite enough. I think Scalaz 8, in fact, needs one more thing, and that's a real software transactional memory implementation that is patterned off of the one in Haskell. So a real STM that's cleanly integrated into IO. And using these two things, you could basically solve all the concurrent state problems you can imagine in a very simple declarative way with very high performance. So resource safely, just real briefly, we're going to rush through this. Sometimes you're going to want to do an action and you're not going to want it to be interrupted. There will be some critical section. I would encourage you not to do this because remember, someone can always pull the power plug on your computer, in which case your uninterruptible action is interrupted. So you have to design with that in mind. But nonetheless, if you need a critical section where you don't want to deal with the possibility of interruption, you just wrap it in uninterruptibly, and you're guaranteed that that fiber will not be interrupted as it executes in that critical section. And this is a compositional definition, so you can nest these inside here, and it has the expected semantics. Bracket is the primitive that you need to use whenever you acquire a resource, because bracket provides a guarantee that anything you acquire will be released, regardless of all the things that can go wrong. So if you open a file, you want to call bracket and specify close file in there as your action for releasing the resource. And now inside the bracket, you can use the file to your heart's content, and you know that no matter what happens, if this fiber is interrupted, or if it terminates for some internal reason, it didn't catch some error that it threw inside, then on the way out, that close file thing is going to be called, assuming that the acquisition of the resource succeeded. And both the action that opens the resource and the action that closes the resource have the guarantee they will not be interrupted. The body can still be interrupted unless you surround it by uninterruptible. So the body could take a long time. In general, you want it to be interrupted. But acquire and release cannot be interrupted, and you have the strong guarantee that if acquire succeeds, release will be invoked. And this happens regardless of how deeply you have nested brackets. You can have brackets inside of brackets, and these guarantees survive. With bracket, you can make the equivalent of finally. And it's as simple as this. You bracket unit, basically, and you call the finalizer in your release, and then you do the this action as your body. And then you have a nice way to get all the same things you would get out of finally, only in a way that's not broken. This is the Scala model for finally. Does anyone know what this prints? Can you guess? No guesses? See, no one even knows what this does. But there's 3 exceptions thrown here. So you can imagine that 2 of them are going to be swallowed for sure. Well, Scalaz 8 never swallows any exceptions. And it does the correct thing here as opposed to Scala, which in my opinion does the incorrect thing here. And this is what it looks like in Scalaz 8. All the errors are reported. 2 of them are reported to the uncaught error handler for the fiber, those that were thrown from the finallys. And then the one that was thrown from the main body, not in a finally, that's the runtime failure that's reported at the top level. So here's another very powerful, and the last one we're going to cover, supervision. So you can take an IO of A and you can supervise it. And that means it's going to be forking stuff like crazy left and right. When that IO of A terminates, when it reaches the end, everything it forked will be cleaned up safely. All those fibers will be shut down in a clean fashion. This means no more thread leaks. And you can use this in combination with fork. If you want to fork some computation out there, you can make sure all of its allocated resources, all the fibers it spawns out, are shut down when it terminates and cleaned up with zero loss of any resources, including threads. And it's as easy to use as this. You just wrap it in the stuff you want to supervise, and at the end of that block, it's going to terminate all the things that were forked off, all the ones which are not currently terminated. So these things actually have algebraic laws. There are ways we can describe these things. For example, we can describe the relationship between fork and join by saying if we fork something and then we immediately join it, that computation can be replaced by the same thing without changing what that computes. So these are more than just operational laws, they're algebraic laws that give you very powerful reasoning across the classes of primitives that are capable of these types of things. All right, so real quick now, just 2 minutes, spend 2 minutes running through this. Performance, so what does this look like? Well, Scala's at 8 I/O is very fast. In fact, it's, as far as I know, it's the fastest purely functional effect monad out there by far. In some cases, it's more than 6,300 times faster than competitors. And this is just the result of sort of optimization, looking at bytecode and minimizing heap allocations and so on and so forth. It's nothing revolutionary, and you can see the code here in a few minutes. But I included future here, even though it's not a functional effect monad. It's a non-functional pseudo monad. But I included it here for reference because you're probably using future. So future is really, really slow compared to Scala's at 8 I/O. Scala's at 8 I/O has all the same stuff in it as future, only far more with far stronger guarantees. You now have a business case to go to your boss and say, look, it's just not pragmatic to use future. We got to rip all this stuff out and use this purely functional stuff known as Scala's at 8 I/O. You have that, like a business reason to go there and to use something that's up to 200 times faster with much stronger guarantees that are going to matter to the business. In terms of safety, Scala's at 8 I/O is very, very safe and doesn't have any implicit executors or mutable implicits. It has that bracket primitive. It has guaranteed async and sync stack safety, even in pathological scenarios. This is a very safe primitive to use. And it's very expressive. It doesn't have a ton of stuff in there. I mean, it has lots of the combinators that I built on top of the core primitives. It just has a few core primitives. But these have the right shape. They're orthogonal, and they can be snapped together to solve all the problems that we encounter in day-to-day programming. So a lot of people are going to say, well, what about FS2? Why not just stuff FS2 on top of an I/O monad to get some of these guarantees? And my answer is no. Because an I/O monad is not a stream. An I/O is a production of one value, and a stream is a production of 0 to many values. You should never use a stream to model something that you would use an I/O computation to do for. And I actually think that FS2, it's a really good streaming library, but nonetheless, it's a sign that we have some work to do in the Scala community. FS2 does not exist inside the Scala ecosystem the primitives, the foundations necessary to build software like FS2, so it had to build a lot of these things itself. And that's sort of reflected in, look at the source code. It has a mini actor library, a mini FRP library. It has a MVAR implementation. It has concurrency primitives. And some of these are actually leaky. It had to build all this stuff because it didn't exist inside the Scala ecosystem, which is a problem we need to fix. This definition of race here, for example, is broken. If you race 100 things and the longest one takes an hour to complete and the shortest one takes 100 milliseconds, guess how long that thing will be running for? An hour. And all those things, all 99 losers are going to be running and doing their effects, sucking up memory and threads. And this is nowhere more apparent than in this timed get method, which is inside ref. So ref is FS2's implementation of MVAR, and it has a timed get. Why does it have a timed get? Well, it has a timed get because you can't layer in timing out with the act of getting, given this definition of an effect monad. It doesn't have the right shape to do that in an orthogonal way. Inside of Scalaz at 8, a timeout is as simple as doing .timeout on your IO action. And it's not just the get that applies to, but it's the put. It's whatever you want. This is truly compositional. And it allows you to layer in the concern of timing out separately from the concern of actually doing these actions. Because these pieces have the right shape, they can be snapped together to solve your problems. All right, so this here is for the 6 people who raised their hand at the beginning. Okay, this is a call to action. I want to say here that 5 years from now, I want to be able to ask that same question and have every single person raise their hand and say, yes, we are all doing pure functional programming. But the problem is, like, I can't get there, like, not by myself. And you can't get there. Like, it's up to us as a community to go out there and to solve the real tough problems that the business needs solving, but to solve them in a way that allows people to reason about their software. And it's going to take all of us, quite frankly. These are hard problems, like taking on some of the software out there. It's going to require all of us working together as one, figuring out how we can show that functional programming does more than just help us reason about the software. It helps solve those business problems. So thank you to, special thanks to Alexi and to Twitter for hosting this talk, and for all of you people for coming to my talk. That's it. I'm going to do the pull request now because I said I would, but I'm totally out of time and they're about ready to pull me off stage. So thank you very much.
I'll let him stay up here to do the pull request so you can watch it. Lunch is being served. So head out there, grab some lunch, and we'll get started back in this room in about an hour. Thank you.
Excellent, thank you.
Yes, thank you for coming.
Thanks. See, I saw that this is pretty much applicative actually. It's not a quantity, it's an applicative quantity. But it's not like expressed like
It is
explicitly.
applicative.
Well, yeah, join does this probably join, all right.
It's a semi-group functor, right?
So, yeah, and I'll kick out my...
Yay! All right, here we go. Ready? Fingers crossed. There we go. Thank you.